The very first episode of Podiatry in Operational Context should discuss the fact that podiatry is a rheological operation. Podiatry in operational context models the fact that the podiatrist has motion over the terrain, and the scientific examination of this synaptic scale motion is the chief concern of this series. We will draw our first concepts of podiatry from the study of rheology, which is the study of the flow of fluids, and then we will associate our podiatry models to the existing frameworks of rheology, which will explain statistical traits of podiatry, such as how fast a podiatrist could feasibly move, and what is the distance or length of the track, and whatever rheological and podiatric topics come from this. Rheology and most of ergonomics are described in relation to the carrier and track model, where the podiatrist is a carrier, modeled as a single point in space, which moves. We will record the motion of the carrier onto a line, which will plot the course of the carrier. Then, we must also describe the geographic features of the land and how they relate to the motion of the carrier, and this domain of examination is called the track. Together, the carrier and the track comprise my core model of ergonomics, which is known colloquially as the carrier and track model, but actually captures the scientific meaning of the ergodic theorem. I first would like to say that the Jacobian measure of motion is an orthotic theorem that says that the podiatrist's motion, which is always plotted as a line, can be topographically unraveled and projected onto a straight line. The rheological examinations will focus on podiatric courses which are projected onto straight lines. There will be a fiber, which models the rheological track in terms of a sequence of individual podiatric segments or steps. The study of rheology will usually discuss the behavior of the carrier in relation to a line segment. This is not to say that these rheological traits don't have real meaning in geographical examinations. This is only to say that we have topographically unfolded and projected a line segment that existed previously in a three-dimensional space onto a one-dimensional manifold for examination. Since the line segment always was a one-dimensional manifold embedded onto a three-dimensional space, the new manifold is obviously isomorphic with the old one. There are different tracks that the podiatrist will walk over. Different modes of examination include the roadster statistics of podiatry, which model podiatric performance on a horizontal level surface. The roadster statistics pertain to tracks that don't have complications such as surfaces that aren't meant for podiatry, and are considered a very stable baseline for examining podiatric performance. The roadster example essentially explains how people perform in perfect conditions, such as on a track and field turf, which is a soft surface with a nearly level pitch, and the whole thing is a long straight corridor without any turns on it. The next topic of discussion will be inclined plane podiatry, which studies the podiatric performance on planes that have 15, 30, and 45-degree pitch angles. This would be considered a very common podiatry application. You should know that when walking uphill, your body will transform chemical energy into gravitational potential energy, and when walking downhill, your body will transform gravitational potential energy into kinetic energy. Some different types of surfaces that are discussed in rheology and podiatry are paved roads. When it was being taught to me, I was told that paved surfaces are the best pedestrian surfaces because you can walk the fastest over paved surfaces. In orienteering, you will also encounter recreational grasses, which are my favorite, and you'll encounter shrublands, which have thorns and stab you. Currently, I am on a grudge over impervious surfaces, such as roads and sidewalks. These impervious surfaces have added pedestrian traits that are negative. The impervious surfaces are hard. They exert a high mechanical force onto your feet, and they cause heel pain. When walking in an operational context, it is my own advice to avoid impervious surfaces. They are exceptionally harmful, since they cause disproportionate wear and tear on your shoe treads. The last topic of discussion for today is the difference between intrepid and tranquil motion. In ordinary orienteering context, a lot of people will be confused. They will be bored. They will stand on the land without much orthotic direction, and they will aimlessly wander around the track area, exhibiting curious behaviors, but not having direct intentions. This is called your orthotic bearing. The orthotic bearing discusses having aimless walking behaviors. During your long-term orienteering operations, you will generate direction. You will march towards your goals, and your new intention is to march towards your goals in an orthotically straight line. This is directed orienteering behavior. The difference between these two modes are known as the orthotic bearing, which describes how smooth the line will become. The two modes of bearing respectively are smooth bearing, which is officially known as tranquil motion, which is characterized as having high orthotic coherence. The other one has rough bearing, also known as irritated motion. The official title for this attitude or behavior, this mode of bearing, is known as intrepid motion, which is characterized by having low orthotic coherence. The higher your orthotic coherence is, the more your pedestrian walk will resemble an operation. I have reached my time limit for today, but rest assured there will always be more. Thank y'all for watching, and until next time, this has been Machine Pencil signing out. Thank you.